Hello, so today I am going to be talking about rope embeddings. So specifically what I'm going to be covering is sinusoidal embeddings, as well as how you can visualize them, visualizing rope embeddings, and spoiler alert, this may be different than how they were explained to you at first. I think seeing what they actually do can be a little bit surprising, but is very useful to cover. Then we are going to derive rope mathematically, and that's going to lead us very nice into how to implement this in code. So, pseudo embeddings were introduced in 2017 when the first Transformers, when the attention is all you need paper was written. And essentially, what these do is you are changing the angle at which you are taking sine and cosine based on I, which is the sentence index, so whether or not it's like the zeroth or the tenth token in the sentence, and D, which is the dimension index. So if your embedding dimension is something like 120, then you're going to have like the zeroth dimension, the first dimension, all and so on up until 120. And this may all seem like a bunch of randomness, but the intuition for why we're doing this is we can think of this as a version of continuous binary counting. So what I mean by this is if we plot the different dimensions of our embeddings, um, and the value on the here I'm going to annotate, and the value on the y-axis as well as the position in the sentence on the x-axis. So you can think of this as like the zeroth token all the way up until like the 800th token if we're doing like a long paragraph. Then the zeroth embedding is going to change really rapidly. So you can think of this as like if we're counting up in binary, the rightmost digit is going to be going from 0 to 1 to 0 to 1. It's going to be essentially increasing very quickly. And you can think of this as almost like a continuous version of this, will rather than always just being at 0 or 1, it's always being at these numbers in between as well, which is going to make it more helpful for doing the sort of math that we do in NLP. And then as we go up, once we get to dimension 10, we're going to have an exponentially longer wavelength. And we can think of this as like binary counting. It's going to be the number way up here, which is only going to change uh, once every few iterations. This is the messiest drawing ever, but I hope you kind of get the point that this is just kind of this one will go here, then here, then here, then here. It will take a while to change. Um, and once we're at dimension 20, it's going to be exponentially longer again. Then at dimension 30, the wavelength is going to be so wide that it almost looks linear. However, if we were to zoom it out again, we'd see that it really is just a really big wave. Um, and here's another visualization, in case this one's easier to see. We can see again, it's almost like counting if we imagine the blacks to be ones and the white colors to be zeros or something of that nature. Then we can see it almost looks like binary counting. Okay, so why did we switch from sinusoidal embeddings? So here's some potential problems. Just a good note that not all of these are solved in rope. For example, no learnable parameters is actually something that rope shares. However, there are like learnable embeddings which have been proposed after sinusoidal embeddings, and have been shown to on shorter sequences perform better. So this can be seen as a potential problem. The main problem, however, that we're really going to be focusing on is this inability to scale to new context lengths. So, we as humans, since we understand counting, we might think, well, because we're kind of just counting in this pattern, wouldn't it be able to generalize? Because you're just always like increasing by the same amount. It's kind of like a learnable pattern. However, I think a good way to think about this is imagine that we have a neuron in a feed-forward network that is always used to receiving input, like the input on this left graph. So you can see that the range is going to go from 0 to 0.15, so it's a pretty small range. And the input is always kind of going to look linear. It's always going to be just in this range, like a very linear value where 20 is always going to be around this area and so on. Now, imagine we scale up the context lengths and that same dimension is being fed into the same neuron. However, now it's looking like this. And we can see here the value has changed drastically. Now we have from 1 to -1, which is a lot different from 0 to 0.15. And we're getting all these different values we've never seen before. And this neuron just really is not going to know what to do with this information. Any pattern it's learned for what to do is not going to be applicable here. And that's going to lead to a lot of problems and errors when propagating this through the model. Um, so let me just clear the drawing. So that is kind of our main intuition for why these can struggle with increasing context lengths. And now we are going to go into the RoFormer, or the rope embeddings as introduced in the RoFormer paper. So before making this video, I watched a lot of other videos on the topic just to see if I could get any other information from it that I missed in the paper. And one thing I noticed is a tendency for people to explain the intuition behind rope embeddings in a way that's not entirely correct. It's almost sort of like wishful thinking. And the main way I've seen it get introduced is this idea of a sort of relative positional encoding, in the sense that, like, the way I was taught is that you have all these vectors and you're rotating them such that the vectors that are in similar positions are going to be rotated closer together to make them have a higher dot product. And the vectors that are in further positions are going to be rotated further apart to make them have a smaller dot product. And what that would correspond to is something like this, where you have zeros in the middle, which means like the position is the same, and so the dot product is like very high, and then it's just going to get lower the further you get from having the same index. However, that's not actually what we do. So real quick, just a couple of things about the Roformer before we get into what's actually happening. Is it's going to be applied only in attention, and it's going to be multiplied rather than added. So if we think about the initial positional embeddings, the sinusoidal ones, they were calculated at the beginning, then concatenated directly to the, or I think it was added actually, to the word embeddings. Then that was used throughout the entire transformer. So in all the attention blocks as well as in all the feed forward blocks. So now we're only applying these in attention and we're going to just multiply them at the time of attention. Um, then I have these little asterisks here for things that are commonly said about them but aren't entirely the case. And I'm going to expand on this third one right now, which is the way it's typically explained as rotating closer things closer together and further things further together. And we're going to see how it actually looks. So, and just to explain what this plot is, I took two matrices populated only by ones and made them the key and query matrices. So you can imagine before applying rope, if we were to multiply these matrices together to get the dot product, we'd get a dot product of 10 in and every single square because we're essentially doing 1 times 1 added 10 times. So we're going to have a very high dot product, which is expected because the vectors are exactly the same. However, after we apply RoPE, if the intuition that we discussed earlier was correct, we would expect the dot product to stay high in all the areas where the positions are close together. So all these middle indexes, which is true, it is very high, it is the highest value here. However, we would expect it to get lower and stay low across all these non-diagonals. So we would expect it to go down and keep going down. However, what we get instead is this wave pattern. And I can actually show this better in another plot. So if we zoom in on just the fourth index of the query here, and we plot different key values for this query index, we wind up with something that looks like this. And here I've only plotted over like 8 indexes, but if we kept going, we'd see this wave going up and down. Um, so this is really quite different than how it's typically explained. It's not saying that the ones closer together are going to have the highest dot product. It's actually just defining this sort of wave across dot products. Um, And if we think about it, this shouldn't be that surprising because if we look at what we're actually doing, it's extremely similar to what the sinusoidal embeddings are doing. So if you look at this m is actually going to be the same variable as this position. They're describing the exact same things, where m is just the index of the query. And then the theta is defined as being 1,000 to the power of -2 I minus 1 over d. So this is almost identical except for the I minus 1. So these two things are also almost identical, -2 meaning it's on the bottom. So the only real difference is rather than just doing cos, cosine, and sine, we're doing cosine, negative sine, sine, cosine. But it's very, very similar. And I want this to be the main takeaway um, from this part of visualizing it, is that I think sometimes the RoPE gets kind of introduced in like this mystical way of like, oh, we're rotating pairs of um, dimensions, and it kind of hides the fact that if we take away all the facts about how it was derived, all the differences and like um, how it was introduced, it's really doing something extremely similar to what the sinusoidal embeddings are doing, with one big difference just being how it's applied, which is multiplied at attention rather than added at the very beginning. Um, and just to really further this point, I promise I'm almost done showing graphs, but hopefully it's enjoyable. Um, if we, before we were plotting the dot product, if we switch gears and plot just each of the individual embeddings, so instead of plotting what happens if we take the dot product of the rotated query and rotated key, now we're just doing what happens when we rotate just the query itself. If we plot the dimensions over sequence index, the 0th sequence index being no rotation, the first sequence index being the first level of rotation, and so on, we can see that each dimension is spreading out and rotating at different rates. And if we plot just the 0th dimension, we can see these same kind of counting waves that we saw earlier. Um, Only now I've just switched how I've drawn the graph. So before I was drawing this part in the x coordinate and this part in the y coordinate, but if you were to flip it, it would be the exact same graph. And if I scale up to different dimensions, we can see that 0 is really fast, dimension 3 is shallower, dimension 4 is really shallow, An important note here is now it's not just that the wavelength is increasing, now also the frequency is decreasing, but it still can be seen as sort of a way of counting. So rather than just when you're farther away, the dot product is higher, it's more like we're still kind of just doing this counting of dimensions just in a slightly different way. Okay. Okay, so now we are going to get into the actual math of the paper. And I'm going to start by just kind of doing some review of some of the basics. So if you're already familiar with all that, you can just skip ahead. And the specific basics I'm going to be talking about is just rotation in general, how we define it in linear algebra, as well as how you can think of imaginary numbers. The reason I'm doing this is just because I feel like a lot of people kind of gloss over this in machine learning and NLP, but it might not be common knowledge to everyone, and I think it is helpful to know and will be helpful when reading research papers in the future. Um, oh, and the reason I have this slide is just to talk about how what the paper is showing, what the RoFormer paper is showing, is they are going to be showing how to calculate the rotational embeddings at the time of attention. So if we have this like query and key, they want to find a way to calculate a rotation embedding at the time of attention. However, if you are doing the same homework assignment that my cohort is doing, you will be tasked with calculating this, which is just the rotation on the query and the key separately. So in this video, I'm going to show how to do the calculation for this. However, if you want to do the calculation for this, it's very simple, and I'll just briefly talk about how to do it at the end, but it's essentially just replacing these m and n variables with just this m minus n variable. Okay, so going now to our little kind of overview of some imaginary numbers and rotation stuff. Let's talk about what this e to the power of I m theta means. So first of all, I just want to say that m, if you remember, is going to be the index of the query, and theta is going to be this variable which is defined in terms of the sequence index and dimension, which isn't super important now. So let's first just talk about how to think about I in general and the role it plays in rotation. So imagine we have this complex number line where we have the real dimension and the imaginary dimension. We can think of I as rotating 90 degrees. And my proof of this is, let's say we have a vector where the first component is 0 and the second component is 1. So something like 0, 1. What happens if we multiply by I? Well, the first the first component is going to stay 0 because I times 0 is 0, and the second component is going to become I. And that's going to be plotted right here, as you can see a 90-degree rotation. If we multiply by I again, I times I is equal to -1. 0 times I is still equal to 0. We're going to get this line here. And we're gonna keep rotating 90 degrees. And any number we have on this plot, if it's like a component of 2 here and 1 here, then we're gonna get sorry, that should be a vector, not a fraction, but we're gonna get like 2i over 1i, and yeah, we're gonna keep going in that way. Um, so what if we want to rotate by like a 45-degree angle? Well, you might think that since since multiplying by I rotates 90 degrees, we can just rotate by 1/2 I. However, what's actually going to happen when we do that is we're going to multiply by 1/2, which is going to just scale the vector down. So if we had a 0, 1 component, this is going to become 0.5. And then we're going to multiply by I, so this is going to be 0.5 I. So we're never going to rotate anything other than 90 degrees. Any other arithmetic we do here is just going to be scaling up or down. So this is kind of the intuition for why we're going to need to use E rather than just using I. Um, because it turns out that E lets us rotate any angle around this complex graph. And the reason for this is that we have Euler's formula here. And essentially what he did was if you break, I'm not going to be able to do this on the spot, but if you break up e to the x in the Taylor series formula, you can derive that you can essentially use algebra to manipulate it to make it into the Taylor series for cosine plus I times the Taylor series for sine x. So that's kind of how he proved the equivalence between these two things. And this is really helpful because this, since we know that cosine of x and sine of x can rotate things, this is how we get the sense that by changing this x value or this theta value, we can rotate by any amount in the imaginary plane. So going back to our earlier example, when we were talking about rotating by 45 degrees, we can do that by e to the I pi over 4. So the reason I went over all that is, oh wait, I didn't delete all my annotations. Clear all drawings. Okay, so the reason I went over all that is because I wanted to show why we're working with this e to the im theta. So you can think of this as rotating in respect to this m theta, which is going to be the sequence index multiplied by this angle, which is going to be defined as a factor of the dimensionality. And it turns out that this identity is going to be really useful because this is going to be a lot easier to work with in code. So this is also helpful because the paper just kind of goes like from this to this matrix, and this is why you can do this. It's because of this identity. Um, so this is what we're going to be working with, but first we need to derive how we get there. So now we're out of the abstract background knowledge section. We're going straight into the Reformer math. So if you skipped over that, please come back now. So essentially, our goal is to get from this to something we can actually write in code. Um, so we're going to start just in the case of 2 dimensions. We have our weight matrix and our x values, and we can just multiply them to get a query vector. Then we want to rotate this by e to the power of I m theta. So this next step here might seem a little bit weird, but essentially what we're going to do is we're going to treat this query vector as if it had a real and imaginary component. So essentially as if it were already a coordinate in this complex grid. So we're going to be treating it as if Q1, this odd index, is going to be the real part, and Q2, or the even index, is going to be the imaginary part, so that we can represent the whole query as being real part plus I imaginary part. And the only reason we're really doing this is just because it makes the math a lot easier. It makes what we're trying to show a lot more obvious. And that's essentially why we do most things that are weird in math, is just to make the math easier. So yeah, we've defined this notation, and this is the notation we're going to use throughout the proof. Okay, so Now that we know that this e to the I m theta can be represented as a product of sine and cosine, we can rewrite it, sorry, a sum, we can rewrite it as e to the I m theta as being cosine m theta plus I sine theta. So here all I've done is I've taken the e to the ix formula and I've just summed out x for m theta. Now, we can also substitute out this q1, q2 vector for the imaginary form that we defined in the last slide as being q1 plus iq2. And then we can multiply that by the cos and sine version of this rotation. So after we factor everything out, so q1 times cos m theta, iq2 times cos m theta, and so on, we end up with this term, and we get two i's, so we can simplify this into -1. And if you look at this term, um, you might notice something. So essentially, we're trying to figure out how we can represent this term as a vector, right? Because we started with a vector, a two-dimensional vector, so we know the product should be a two-dimensional vector. And you might notice that we can actually break these terms into two parts. We have these two terms which are factors of I, or are imaginary terms. Then we have two terms that do not include I. So going back to our earlier notation, how we defined it previously with this qi, q2, we can rewrite this product as a vector where the first term is the real term and the second term are these imaginary terms. So we're taking the I out, just matching our earlier notation where we don't have the I here, although we do have it here, and we get this product. So just to kind of summarize again, so basically what we've shown is that in the two-dimensional case, q1, like this vector times this rotation equals this product. And our goal was to find an easier way to represent this rotation. So now we know that this vector and that rotation leaves this product, we can work backwards to find an easier rotation that would give us the same result in every case. And it turns out that this is just the dot product of, sorry, it takes me a second to clear my drawings on Zoom. This is just the dot product of this matrix. Um, And you can try it on your own if you don't believe me, but it's very simple. This is just what you get when you multiply these two matrices together. So this is how we get the main matrix that's shown everywhere in the Roformer paper. Um, sorry. So like, okay, do I not show it? Maybe I just don't show it yet. But if you've read the paper, you'll see this matrix everywhere. It's essentially like the bread and butter of the paper is this rotational matrix. And this is how it's derived. So this is kind of the crux of the whole paper. If you've understood up until this point, we're essentially just going to be taking like very small steps, building off of it for the rest of it. So definitely, like you've done all the hard work in terms of understanding thus far. Um, so now we're going to go up to multiple dimensions. So far we've only been working in the two-dimensional case. And I don't know about you, but when I think about something rotating in two dimensions, it's a lot easier than thinking about like a 45-dimensional being rotating about in space. Um, and I guess whoever wrote the paper agreed with this, and so they decided to define it rather than the whole dimension rotating. We're just gonna break each embedding. So if we have embeddings like 1, 2, 3, 4, all the way up to some embedding dim, I'll just say like 120. we're going to break these up into pairs and only rotate each pair. So if we think of each of these pairs as vectors, and we're just going to be rotating like each of the pairs, so we're still always doing two-dimensional rotations. Um, then the final vector is just going to be the rotation of all those pairs. And how they define this mathematically is using this matrix where the rotations are on the diagonals and zeros are on the off diagonal elements. So in case this kind of confused you, it's okay, I'm gonna work through it. So if we have our query going from 1 to 4, so a four-dimensional one, then once we do the dot product with this diagonal matrix, we're gonna get the first term just in terms of Q1 and Q2 because the Q3 and Q4 terms are gonna be multiplied by zeros. That was the worst. You're like this going here and this going here. Um, so these are just gonna be zeros. Then again for here, if we go through these terms, these two front ones are just going to be zeros. So we're going to end up with a single vector where the Q1 and Q2, this pair is going to be its rotation is going to be first, and then this pair's rotation is going to be second, and so on and so forth, which is what we wanted. So here is going to give us to the major intuition for what we're going to actually be doing in code. Because so far, everything I've shown, it's maybe you can like take a guess at how you would do it in code, but it would involve like a lot of inefficiency, a lot of like creating weird matrices. But here's the part that really kind of sells for why this is easy to do in code. And that is that we can see a pattern between the rows that I've drawn in pink and the rows that I've drawn in green. And in fact, if we imagine that we have a vector where we've stored all the real components of each query, so all the odd components essentially, and another vector where we've sorry, I should notate this. Then another vector where we've stored all the even components, then we can calculate all the odd rows just by doing this cosine m theta once we've calculated the m theta values times query real minus sine m theta times query imaginary. And we can do the same thing for the even rows. So essentially, in just one equation, we can calculate this entire matrix. We can calculate all the odd rows and all the even rows. And all we would have to do at that point is just reshape it to make it the same shape as the original query or key, and then we'd be completely done. So this is kind of the intuition of like the end goal for what we're going to want to accomplish in code. Breaking this up into parts. So step one is we're going to have to create this query real and query imaginary vectors, where it's just going to be the odd and even indexes of the dimensions in the query. And then we're going to calculate this theta tensor given the formula, which is essentially just 1000 to the power of -2, then this I, which is just from 1 to the to half of the embedding dimension because we're splitting them into pairs, so it's only ever going to be half over the total embedding dimension. So that's just going to be extremely like we're just going to use a simple formula to calculate that, and it's not going to be too tricky. Then we're going to multiply the theta tensor by each m value, which is our sequence index, which will give us the angle that we're rotating about. So that's the thing, if you can see all these sine and cosines are in terms of m theta, that's essentially what we're going to be calculating in that step. Then from there, we're just going to find the sine and cosine of each of these angles and save it as a variable. Then we're going to calculate the odd and even rows given these formulas. So how do we actually do this? So if you are doing the same assignment I was doing, you will have a line of starter code that looks like this. And essentially what this is doing is reshaping the last dimension, which is going to be our embedding dim, to form pairs, which can be interpreted as the real and imaginary representations. So essentially, okay, zoom. So essentially, we can kind of think of the shape of our query as being batch size, sequence lengths. I'm sorry that this is so slow. I'm doing this on a trackpad. And then our head dimension, which we will go more into later. For now, you can just kind of ignore it, but it is going to play a big role later. And embedding dim. So, what this is doing is it's taking the last part of the shape, which is going to be our embedding dim, and it's going to be reshaping it to that shape turned into pairs, which is represented by this -1, which means change this dimension in whatever way you see fit, then this 2, which means make it into pairs. So it's essentially going to turn this into, oh God, why did I make myself typing right again? But these same things here, and then this embed is going to be have a shape of 2 now, so it's going to be in pairs. So you can think of it as like embed 1, embed 2. Yeah, I just said it, so I don't need to finish typing it. And then after we get this embedding dimension split into pairs, we're going to do this unbind, which is going to take the first and second part of each pair and group them together. So this is how we're going to get the query real, ending up with all the odd parts of each pair, which is going to be all the real components of this vector we're defining. And the query image is going to be imaginary. It's going to be all the even parts of those pairs. So why is this? Sorry. Oh, right. Okay, I didn't draw those. Those were already there. So now we're going to calculate our thetas. I did this by first calculating I, which I just did as torch.arrange 1 to the dimensions of our query, which is just going to be this, oh, I erased the drawing, but it's just going to be the third component of the shape of the query, divided by 2 plus 1, which is just going off this I thing here, and it's just going to be of type torch float. Then we can use the i's to make the thetas. Again, this should be pretty self-explanatory. I'm just copying the direct formula there. Then we can create m's, which represent the sequence index. And once again, this I think is pretty self-explanatory, just going from 0 to the query shape. Then this is a part that might be a new PyTorch function, so I'll explain it a bit. So we're going to use this einsum ij goes to ij, which essentially creates a matrix where each element ij is the product of the I of the first parameter and the j in the second parameter. So it's essentially going to take vectors and create this matrix. And I've shown here a little example where you can see that 10, 20, 30 is, you can see there like the i's, then times 1, it's just going to be the same numbers, and then times 3, it's going to be 30, 60, 90, and then times 5, it's going to be 50, 100, 150. So this is just kind of going to create an array with the products of all the sequence lengths and all the theta values, which is what we want when we're calculating m theta. Okay, so up until this point, I haven't really gone over the head number because it wasn't infecting anything we're doing, but now we are going to need to talk about it. So just a review of what I mean by head number is when we have attention, we're typically not just doing one attention head, we're going to be doing a bunch of different attention heads in parallel. And each attention head is going to be initialized with a different weight vector. So the values are going to be slightly different for all of them. So we're not just going to have one query, we're going to actually have several different queries for each sequence length. So if we have like batch size here, sequence lengths, maybe we have like maybe we have 2 tokens per sequence in the batch. A batch size of 1 maybe. Then let's say half our embedding dim. The reason this is halved is just because we're splitting them up into pairs. Let's say this is something like 1, 2, 3, 4, 5. We're gonna have this other row here, whereas if this is our embedding dim is 5, then we're gonna have a different row here for the head number. So this might be our embeddings for the first head, and these 5 are going to be our embeddings for the second head, which might be slightly different because we had a different randomly initialized weight vector. So that's kind of how you can view the visualization of what this tensor is going to be. And this is going to affect us because, okay. So usually PyTorch already helps us a lot by projecting over batch dimensions when multiplying a 2D tensor by a 3D tensor. So this is going to happen a lot. Anytime you use MapMule, it's going to automatically do this. It's going to help us a lot when calculating attention by scratch. However, this head num, PyTorch isn't going to help us do this automatically. We're going to need to actually physically project over this head num. So essentially, in why I say we need to project is because even though these queries are going to be slightly different depending on the heads, the m theta values aren't going to change dependent on the heads, right? Because theta, as we can see here, is only dependent on the dimension, and m is just going to be dependent on the sequence length. So nothing is really dependent on these embeddings, so we can just project over the head num. So how we're going to do this is when calculating the cosine and sine angles, we are going to unsqueeze, which is just going to add this dimension as 1. I talked about this in my other visualizing in PyTorch video, but you can kind of think of this as just adding a bracket. So yeah, if I draw this as batch size, sequence lengths, then typically I just have the embeddings here. We can just think of this as just adding brackets along the embeddings and not doing anything with it yet. Then this expand is we're actually just going to project the same thing over head num. So if head num is 2, and let's say we had like 0, 0, 1 in here, then we're just going to duplicate this same embedding over how many head nums we have. So if head num is 2, then we're just going to do it twice. And what essentially this is going to amount to is every different vector we have for each of the different heads in our original query matrix, we're just going to multiply them by the same vector. Okay. And we're gonna do the same thing with sine. Okay, so now we get to doing the last part of the mathematical intuition. We're going to find the odd and even indexes by multiplying these values by the imaginary parts of the key and the real parts of the key. And just a side note, this entire time I've been using query. I'm not sure why I decided to use key here, but they're going to be completely identical. The only difference is going to be the variables you're like the names essentially. Um, okay, so that's great. Now we have all the even rows and the odd rows. But how do we get it to look like an actual matrix if we want to just return the rotated query vector? So essentially we're going to use this command here. So what it does is it's going to stack these even indexes and odd indexes among the last dimension, which was embedding dimension, which is essentially going to create that same thing we had originally. So if we remember way back, way back here when we're kind of creating pairs for the like the odd and even, we're kind of doing that same thing here. And we're going to be just stacking them on top of each other. So we have odd 0, even 0, odd 1, even 1, odd 2, even 2, and so on. Then when we reshape as query, we're essentially going to be just flattening these pairs into the same shape that they were originally, which is just going to be like the normal query shape where everything is ordered in the way we would want them to be. So that's the full intuition for what we're doing in code. And again, this is just for taking a query in and sending out the query with rotational embeddings applied. Um, so this is true. If you are going to copy it, change the names. That's always a good note when copying code from the internet. Um, so uh, you might be thinking, okay, that's great for calculating just the rotation of the query and the key separately, but what if I want to do it like the original paper does it, which is doing everything at the same time? So this is actually extremely easy. All you're going to do is use this rotation matrix, and by rotation matrix, I am referring to this thing. You're going to use this during attention in this formula here. Oh, in this formula here, except instead of using m, which was the index along the sequence of the query, you're going to be using n minus m, which is the index in the query minus the index in the key. So that's kind of going to be like the relative index between them. And this is going to be mathematically equivalent to doing it the other way, but it's going to be slightly more efficient when doing it in code. Okay, so now we have a few disclaimers. I didn't have as much time to research this as I would have liked to. However, it is interesting to note that although RoPE is quite widely used now, it's kind of recognized as one of the best, I would say, positional embedding, or at least the most used, with an asterisk, because there's still a lot of other ones being used. It doesn't really do the thing that it set out to do, which is to help with longer contexts. However, there have been several variations on RoPE that do help fix this problem. And most of those variations involve some form of mapping the new context length into a place similar to the old context lengths. So as you can see in this position interlopation, we have this L prime, which is the new context window, and you're dividing L by L prime to kind of get this, like, it's almost sort of like a modular position where it never goes past the old position, it just kind of loops back. And that has been shown to work better for increasing context lengths. There's also a variant called yarn. I wanted to research this, I did not have time. Um, but I believe this is what's used in llama. And it's another similar but slightly more complex way to kind of map the new context window into the old context window when using rope embeddings. But you can read about this on your own if you are interested in it. And yeah, as you can see, I prepared a really nice summary ending slide. And thank you so much for watching, and please consider liking and subscribing because these videos do take quite a bit of work to make. Thank you.